Swayam Prabha. Digital India. Educated India.
So we defined our basic probability space, which consists of omega, sample space, f, set of all events, and p, a probability function defined on set of all events. And then we call our probability space to be discrete when omega is a discrete set, that means either finite set or countably infinite set. And when defining random variable, we are given given a probability space So we are given a probability space omega fp, and using that I am defining a random variable. And what is it? It's a function from omega to r, so that the inverse image of every interval is an event, so that we can talk about the probability of x being within some interval, and it turns out that is enough. Okay, and then we talk about mean or expectation of a random variable, of a discrete random variable, and if omega is finite, then it's just you define sum over its image set of x, probability of x times x. It's really a weighted average. For omega, if omega is a countably infinite set, then we define expectation of x exists if expectation of mod x converges, and in that case expectation of x also converges to a unique value, unique real number, and that is defined as the expectation of that real number. And then we move to questions like how probability is concentrated around its mean and so on. And then we sort of proved our first and the most fundamental result in this context, which is Markov inequality, which assumes that the given random variable x is positive and expectation of x exists, and then it says that the probability that x takes c times more the value of its expectation is less than equal to 1 over c for every real number r. And we saw the proof for the case when x is a discrete random variable, although the theorem holds for continuous random variable for any random variable, but the proof we did for only discrete random variable. So if you have any question, you can ask me, otherwise we move on to another concentration inequality, which is called Chebyshev's inequality. Yeah. Probability of an event. Sorry, here of an event. Probability is x greater than equal to c times. Correct. A set of images. Yeah, it's a subset of real numbers. Yeah. Exactly. So that's why I said that that's a very good question. Her question is, let me reiterate the question. I am writing p of x, where x is a real number, whereas this p is defined on events. Yeah. See. Yeah. And here is the mapping. So, so let me write PR. So we define probability of x equal to A is the P of the event of this event, that look at the set of all omega who are mapped to this real number A, and the probability of that event is, we are calling it probability of x equal to A. So let me that's a very good question. And let me write it here, that not maybe P of x, maybe I should write just following the notation, probability that capital X equal to small x, and same goes everywhere, same goes everywhere. Sure, that's a very good question. Yeah, 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 of course I can give. And yeah, so let's not do Chebyshev inequality, and let's see some examples. So suppose so say toss a fair coin say n times. Sure. And let's define a random variable. So if I toss a fair coin n times, and suppose I am interested in finding how many times it comes head and how many times it comes tail. Sure. And say we define a random variable xi to be say 1 if say ith toss comes head, and -1 if ith toss come tail. Sure. So here also see the underlying probability space and the random variable. So underlying, if I look at the underlying probability space, for every toss, for every coin toss, the underlying sample space has two outcomes, head and tail, and the random variable xi is a function from underlying sample space to real numbers, and this is how I am defining the mapping. If for the underlying sample space value to be head, the corresponding real number I am assigning it to 1, and if it is tail, I am assigning it to -1. So what is the probability that x takes 0? That's the probability of empty set. Inverse image of 0 is empty set under this definition of xi, and the probability that xi is 0 is 0. What is the probability that xi takes value 1? Inverse image of 1 under this mapping xi, which is head, and if it is a fair coin, then the probability is half. What is the probability that x takes value either 1 or -1? So then look at the set 1 and -1 and look at its inverse image under xi, which is the whole sample space, and its probability is 1. Sure? Okay. And okay, and let x so let me change this definition a little bit, say 0. Suppose if it comes tail, I define it to be 0, just a function I am defining, and now let x be the now I am defining another random variable x. It is the number of times that head appears. Now this random variable is defined on underlying sample space where so here is my sample space x omega, this is omega, and what are the sample points? Every sample points gives an outcome of n tosses. So maybe this point may be that the first toss came up head, second toss came up head, third toss came up tail, and so on. So possible outcomes of every n things. And this sample space, this random variable x maps this set to a real number, set of real numbers. And what it does, it's again it's a function, and it counts the number of heads. Suppose this point may gets to some numbers, say I don't know, n by 3 or something. So left side is the sample space, and right side is the real number, and x is my random variable. And f is, because it is finite set, f we are defining it to be 2 to the omega, and now it is sort of obvious that that if I take any interval in this real number, its pre-image has to belong to f, because it's a subset of omega, and every subset of omega is in f. So it's a valid random variable. Okay. Okay. Now suppose I want to compute expectation of x, right? So if it is a fair coin, then what is sort of what should be the expectation of x? What does our intuition say? What can we expect on an average? How many times it should come up head out of n times? N by 2. So we want to prove that expectation of x is n by 2. This is to prove. Right? Okay, of course we can simply apply the definition, and we can write that expectation of x is again from the definition that look at all points in this image. So the points in the image is from I equal to 0 to n, because others are not in the image, and I times probability that x takes value I. Sure, that's how it is defined. It's finite, not even countably infinite, it's finite, so you don't need to worry about convergence and those sort of stuff. This is how it is defined. And now this is what is probability of xi. I look at this point I and find the set who is mapped to I, right? That's how it is defined. So what is the who are the elements in omega who are mapped to I? Exactly I heads should come. That's how the function x, the random variable x, is defined. Now I can come into so I heads can come in n choose I possible places, isn't it? Because there are n tosses, and among those n tosses, I tosses should come up head, and the probability that those I tosses come up head is 1 over 2 to the I, and there are also n minus I tosses, they should come up tail, and that probability is 1 over 2 to the power n minus I. Sure, I am just computing the probability of this set. Sure. And now this is what? This is 1 over 2 to the n. So this comes out. N was fixed. Yeah, correct. So I equal to 0 to in I times n choose I. And again, using high school math, it can be proved that this expression is n times 2 to the n minus 1. You do usual calculus, write the binomial coefficient, those theorem expansion, and differentiate with respect to x, put x equal to 0, 1, what is appropriate, and this, and so this is n by 2. Question. But you know, this calculation is already pretty messy, and this can be simplified using what is called linearity of expectation. Let's see what is linearity of expectation. Okay, so first observe that x can be written as this sum x1, x2, xn, sum of these n random variables, because x1 takes 1 if the first coin comes up head, x2 takes 1 if the second coin comes up head, otherwise 0. So the sum actually counts number of times it comes up head, isn't it? So x is equal to x1 plus x2 plus xn, and also it is very easy to compute expectation of individual xi. Let's see what is expectation of xi. Xi takes only two values, 0 and 1. It takes value 1 if it comes up head, which happens with probability half, and it takes value 0 which also happens with probability half if it comes up tail. So this value is half. Okay. And now what linearity of expectation allows us to do is that expectation of x is of course this, because x is x1 plus x2 up to xn, and linearity of expectation says that you can push expectation inside. You can interchange the sum and expectation. You can write this as this is by linearity of expectation. Okay. And now it's very easy, because I know expectation of x1 to be half. Expectation of every xi is half. Isn't it? And that's it. So to prove linearity of expectation, so what is linearity of expectation? Let's write properly, formally. That if you have n random variables, then that expectation of, So what are the assumptions? We have n random variables, and their expectation exists. Expectation of x1, these expectations exist. Also some. Right? Then what happens is that sum gets pushed into. Okay? I leave the proof to you. Just you follow the definition. Just give a important hint, not hint, that it is enough. Observe that enough to prove for n equal to 2. Although the statement holds for any n, we are given a natural number n, it's enough to prove for n equal to 2. And you see why? Because you can apply many times and apply in times or in minus 2 times, and then you will get this result. And to prove this for n equal to 2, you just use the definition of expectation. Just write those definitions and just play with these summations and it will come out. Okay, so I am leaving the proof to you, and let us see how we can apply Markov inequality for this random variable x. It satisfies the conditions of Markov inequality. Does it satisfy? Not, it does not satisfy, right? Because it can take 0 value also. So, actually, so let's replace this condition x is positive by non-negative. Then at some times our proof breaks, right? Because for example, we use that x equal to x is positive to cancel expectation of x. Any fix? Is the motivation clear? That we want to apply this Markov inequality to the odd example of coin tossing, but that can take x takes value 0 also. So basically we observe that we don't even need this stronger assumption that x is positive. Even if x is non-negative, then also Markov inequality holds. Can anyone suggest a proof or fix to the proof? Because we have used, for example, we have cancelled expectation of x and argued that it can't be 0 because it is x is positive random variable. Any fix? So here is the thing. This proof is fine, and if x is positive, only if x takes value 0 with probability 1, then only it fails, right? So if x takes value with probability, it takes positive value with some non-zero probability, then expectation of x is positive, and nowhere else we are using this. So for this proof we assume, so this write it case 1. Case 1 is probability that x equal to 0 is not equal to 1. So it takes care of almost everything. and it leaves a tiny case, that case 2 is that probability that x equal to 0 is 1. But if probability of x equal to 0 is 1, then obviously it satisfies this inequality. The probability that x is greater than equal to something greater than equal to 0 is actually 0. No, sorry, I am missing something. Yeah, if expectation of x is 0, then also it does not satisfy. So let's x exists and expectation of x is not equal to 0. Because if expectation of x is equal to 0, then probability that x greater than equal to 0 is actually 1. So let's assume expectation of x is not equal to 0. This is really a marginal case, and for case 2 it's a contradiction. Because expectation of x is 0 in this case. Okay, now we can apply this theorem to our case, that x can take non-negative value, but we have calculated expectation of x and it is n by 2, it is not 0, and it takes non-negative values. So we can apply Markov inequality and get, say, by Markov, we get that probability that x takes value 1 plus epsilon more than expectation of x is less than equal to so it takes value 1 plus epsilon times more than expectation of x is less than this, less than 1 by 1 plus epsilon. For example, if we put epsilon to be 10, then it takes value 11 times more expectation of x is 1 over 11. And we say that this bound is little weak, because look at, for coin tossing, what does it give? It, for if I put x equal to say 3 or x equal to 2, sorry, omega epsilon equal to 2, then it gives that probability of x is greater than equal to 3 times n by 2 is less than 1/3, whereas we know that its probability is actually 0, isn't it? We have tossed coin n times, it can't come out head 3n by 2 times. That's why we call it weak inequality. But I leave it to exercise or for tutorial brainstorming that with the kind of assumption that Markov used, this is the best one can hope for. What do we mean by that? That there exist random variables which satisfy those properties and for which Markov inequality is actually equality. What do I mean? That this Markov inequality is tight. It can't be improved. Tight means it can't be improved. Can't be improved means that the right hand side can't be decreased further. No, right hand side is giving an upper bound on the probability, and the smaller the upper bound is, it's better. But I am saying it is tight. In the by that I mean that the right hand side can't be decreased further. Now, why it can't be decreased? Because I can give you an example of a random variable x which satisfies the two properties for these two random properties for these two assumptions of Markov inequality, and this inequality is actually equality. So if you can reduce, then for that random variable x, this theorem does not hold. So it is, take it as a exercise that find an example of a random variable x for which this is tight. So But then am I not contradicting myself that when I sort of told that next we will look at more non-trivial stronger inequality. Stronger means right hand side I had to reduce. Those stronger inequalities also assume more thing. That means that look at the assumptions of Markov inequality. I am claiming Markov inequality tight because with this assumption you can't reduce the right hand side. So assume more and reduce the right hand side. That's the gain. The more you assume on x, the more you can reduce the right hand side. That means you are getting stronger and stronger inequalities. Everyone with me? Question? And that's the motivation to get a stronger inequality. And let's see, our next inequality is Chebyshev's inequality. Yeah. What does it assume? It does not assume x to be non-negative like Markov. It sort of leaves that assumption, and but it assumes that expectation of x and expectation of x square exists. So Markov only assumed existence of expectation. It assumes existence of both expectation and variance. Expectation of x square, if it exists, then variance also exists, because just recall that variance of x is expectation of x square minus expectation of x whole square. So if both expectation of x exists and expectation of x square exists, then variance also exists. So here is the extra assumption that the Chebyshev's inequality is making. So this is assumption, and then what do we have? Then Chebyshev says that yeah. I think I'm messing it up. Let's see. So it says that probability that x deviates from expectation of x by c times variance is less than equal to 1 over c square. This is for all real number c. Sure. And let's prove it. C times square root of variance, I think. Yeah, let's prove it. But let me recall the definition of variance. Variance of random variable. So variance is defined as variance of x is expectation of x minus expectation of whole square. So you are given a random variable x. From that you you take expectation of x minus expectation of x whole square. That means in the definition of expectation of x, you replace small x with small x minus expectation of x whole square. While calculating expectation variance of x, think of expectation of x as a constant. Given x, expectation of x is nothing but a constant. So it's really x minus some constant whole square. It's not that crazy as it looks. Okay, now let's prove it. Yeah, C is positive, sorry. C is positive. Yeah. Because the left hand side is positive here, this left hand side is positive, and if right hand side is negative, then it has to be probability 1. Yes, so C is positive, that's true. Okay, so let's use into the proof. So, so probability of mod of x minus expectation of x. This probability I need to study. The first step is let's remove the mod. And how can I remove the mod? Just square both sides. Sure. And so this is same as okay. And then C square. And now apply Markov inequality. Markov inequality for this random variable. This is a square, something square, so it has to be non-negative. And so by applying Markov, what we get is less than equal to and look at variance is nothing but expectation of this random variable by definition. So it's basically saying what is the probability that this random variable takes value less than c square minus this. For Markov, sorry, what I'm doing? Yeah, this was greater than. Why I have written less than here? This is greater than equal to. This is greater than equal to. Sorry, it was the greater than, maybe greater than equal to begin with. Sure. And now then by Markov it is 1 over c square. Maybe I should write on the line that probability that x minus expectation of x whole square is greater than equal to c square times expectation of this quantity, x minus expectation of x whole square. Now it is Markov, and this is what? So this will be equality. Again, this shows relation from the last line with the last line, and this is less than equal to 1 over c square. Question. Okay. Now let's see why we call it a stronger inequality than Markov. Let's see what concentration it gives for for the coin tossing example. Sure. So for coin tossing, so let's go back to coin tossing example. So we saw that recall x, saw that expectation of x is n by 2, right? And what data we had, x equal to x1 xn, and we also had that expectation of xi is half, right? Okay, and now to apply Chebyshev, where here the right side is we have variance, right? So we need to compute the variance of x. And yeah, so variance of x is, so x is nothing but x1 plus x2 up to xn, and now it would be excellent if we can push this variance inside. If we can write this sum as variance of x1 plus variance of xn, because this computing variance of this xi's is very easy because it takes only two values, 0 and 1, whereas directly computing variance of x is always difficult. It takes so many values. But this equality is not true in general. You cannot push variance inside like expectation. That's bad news. But the good news is in this case you can push. So we need to write a reason that x1 to xn are independent. So if you are summing independent random variables, then variance you can also push inside summation. So this is sort of okay. And now it is very easy. Let's compute variance of xi separately. So what is variance of xi? Let's compute from the definition so that we get all used to. So it is what? Expectation of x minus expectation of x whole square. Okay. Xi. What was expectation of xi? It was half, right? Here it was half. So let's put half here. As I was telling before, it is basically a constant. And now xi takes value 0 and 1. If it takes value 0, then this quantity is 1/4, and this happens with probability half, plus it also takes value 1, and if I put xi equal to 1, then also it is 1/4, and the probability is also half. This is 1/4. Okay. So variance of xi is 1/4, and now from this inequality, what we have is that variance of x is nothing but sum of these variances. So we have that variance of x is nothing but n by 4. Sure. So we have variance of x also. And let's see, now we apply Chebyshev to our coin tossing example, and we were sort of interested in the probability that x takes value more than 1 plus epsilon times expectation of x, isn't it? Markov gave 1 by 1 plus epsilon. Let's see what Chebyshev gives us. So let's put expectation of x other side, because that's what the left hand side looks like for Chebyshev. And this is less than equal to right. Can anyone explain why it is less than equal to? Because look at this event. This event is a superset of this event, the event earlier. This, if this is event 1 and this is event 2, then event 1 looks like a set, this set, and event 2 is a superset. If event 1 happens, then event 2 obviously happens, but not the otherwise. So the probability of event 2 is at least as high as probability of event 1. Okay, now this question. Yeah. Okay. Now to apply Chebyshev, left hand side we have in shape. On the for the right hand side we need to write it in terms of variance, so that we can apply Chebyshev, and let's do that. Again, this is equality because this is relation with previous line. Let's put the value of expectation of x. It was n by 2. Okay. And we need to write in terms of square root of variance. Square root of variance was n by 4, and we need to write in terms of square root of variance. Yeah, here, square root of variance. So let me write it. Correct. So this is my C, sort of, a constant C. And now we apply Chebyshev. And get what? Less than equal to 1 over this constant square, 1 over epsilon square n. Now look at this. This is right hand side is much smaller. For Markov, compare with Markov. What compare it with Markov? Markov gave 1 by 1 plus epsilon, whereas this is much smaller, especially if n is large, right? Any question? And this sort of framework is so common in applications, like, because think of, you can think of like a sort of, suppose I give you a randomized algorithm. I give you an algorithm for a problem which sort of fails with, say, 50% probability, but you can check whether it has failed or not. Just see another concrete example, because the same thing as coin tossing, but in a framed in a different way. I give you a algorithm for, so let me write. So suppose an algorithm solves or decision, not solves, suppose you have a decision problem. Decision problem means that any problem whose answer is either yes or no. That's what decision problem is, right? And think of, say, SAT. We are given a Boolean expression, and the question is, does there exist a satisfying assignment? It's a decision problem. And we are given an algorithm which solves this problem with 2/3 probability. Now, how can, from this algorithm, I can have another algorithm which solves this problem with 99% probability? It's very easy. You run this algorithm multiple times, n times, and and answer the majority. Suppose answer the majority. That means you run the algorithm 1,000 times, and and see how many times it gives yes answer, how many times it gives no answer, and if it gives more yes answer than no answer, output yes. And again, using the same calculation, it's like tossing a coin which comes up head with probability 2/3, isn't it? And then your expectation will be not n by 2, it will be n by 3. Your variance also will change appropriately, but what is important is that what this Chebyshev's inequality shows is that if your n is really large, then your value of this random variable x is tightly concentrated around expectation of x. So with very high probability, if n is large, then 2/3 of the time it will give a yes answer. So your majority of the time you will get yes answer, and that probability is really high. So for example, if you choose to be your error probability to be 1% or 0.1, say, just put 1 over epsilon square n to be 0.1, right? And then just find out n. And these things are very important in surveys, even in your simulations. You don't know how many times you need to run your experiment to be sure, how many times, for even for this sampling case, how many voters you need to sample to be able to justify, to be able to know the what fraction of time it came up, what fraction of voters has voted for party A, and so on, right? So let me end this with fraction of t, with this, just going back to our motivating example of party A and party B, what fraction of things. So that's an example. Actually, although I'm writing example 1, 2, 3, they are the basic framework is same. Now let's go back to our motivating example, that we have a population of size n. And there are two parties, A and B, and say if A is the fraction of population voting for A, similarly if B voting for B. Sure. And say assume if A is greater than if B. One has to be more than other. The sum is 1, if A plus FB is 1. So let's assume they are not equal, there is some gap, if A is greater than FB. And let's see, maybe we can have a rough estimate on how much samples we need to draw. So what is our algorithm? Our algorithm is, let's draw few samples. So okay, so here is my algorithm. Algorithm to predict who wins. Obviously A wins because we have assumed if A is more than FB, but my question is my algorithm will my algorithm predict correctly or not? That's the question. And let me tell you an algorithm. Very simple algorithm. Sample uniformly L voters with replacement. So basically says that, what does this mean? You close your eye and pick a random person from the voter and see whom he or she votes. Then again put her back on the population. Don't keep her out. That's what we mean by with replacement. Put her back in the population. So there is chance that my second in the second row also the same guy may have been picked. That's fine. Again and repeat this for L times. Repeat this for L times, and see who wins in this L votes. So maybe let's write if f hat of L, f hat of A is the fraction of samples voting for A for B, right? This is the fraction of samples who vote for B. And so our algorithm succeeds if f hat of A is greater than f hat of B, isn't it? My algorithm will just see what fraction of people voted for A in my sample and what fraction of voted for B, and if more people votes for A in the sample, it will predict that A will win. That's my algorithm. So succeeds this and fails if f hat of A is less than f hat of B. You can assume L to be an odd number so that there is no tie. And we want to calculate this thing, these events. What is the probability that my algorithm fails? Yeah. Sure? Everyone with me? Okay. So let's compute. Shall I compute or leave it as an exercise, or you try today and let me do it tomorrow. Let me assure you that all the material that you needed, all the tools that you need for this thing, it's already there. We have already covered today. So you need to use those inequalities, do some expectation analysis, variance, whatever you need, and find out. And what you will see, you can prove yourself that. So okay, what is our goal? Our goal is to find out L such that probability of failure, say, is less than, so I don't know, 0.01. Failure probability is 1%. With 99% probability it succeeds. So this is the question. Compute the L so that this probability is less than 0.01. And you will surprised to see that L will be independent of capital N, the size of the population. It does not depend on capital N. And that's it. So we have proved in that case that the sample size does not depend on N. Okay? Okay, so let's stop here and yeah, let's see. Let's continue tomorrow from here, and I hope some of you should be able to solve this. Okay, thank you. Scroll up or down, down. Algorithm is very simple. This is the algorithm. Sample L people uniformly at random and look at the fraction. Whoever wins in my sample election is my winner. This is the algorithm usually followed in all this opinion poll, prediction, and this sort of thing. So compute the value of L. How many times I need to sample? Obviously, the more I sample, the more my error rate goes down. So that's why I gave you a specific error rate. I want to achieve my error rate to be less than 0.01. Tell me how many samples I should draw. And the price is you will be see yourself that L does not depend on capital N. Okay, question? Yeah. Sorry? Yeah, so that's a very good question. Why do we sample with replacement? We can sample without replacement also, and the result will remain same. Only the proof that it remains same is little non-trivial. You can also sample L people without replacement. That means you sample one people and put that people outside the population so that you don't sample him or her again. And it turns out that the number of samples in these two scenarios is almost same, but the second the scenario without replacement, that means you don't put back the sample voters, is little more involved than this one. This analysis is very easy. Why little more involved? Very easy reason. If you with replacement you are sampling from the same distribution, and these corresponding random variables are independent. It's like independent coin tosses. Whereas if you put him or her outside, then it is not independent. For example, if I sample you for in the first thing, then probability that you will be sampled in the second iteration is 0. So then individual samples are not independent. They become dependent, and then calculations is little more non-trivial. But it's a good question. Question? Yeah, sorry. Also, you can find this material written more formally and properly in my web page. You can just Google my name. You will go to my course web page, and there is a course that I offered last semester called randomized algorithm. It's available on my web page, on my home page, and there you can see these things. You can I encourage you to read those material, where the same things are written much more formally with many more examples and so on. Questions? Okay, great. Yeah, thank you.